Hello, in this short video, I'm going to explain a simulation for measuring the performance of different page replacement algorithms when it comes to virtual memory in operating systems. So this is a C program that I have created. Basically, it's a test bench for an algorithm called the optimal page replacement algorithm. But the same test bench can be used for measuring the performance of other page replacement algorithms like the second chance algorithm or least recently used algorithm, so on and so forth. I'm going to go over the program and show you how it works. But before doing that, let me briefly tell you how this simulation works. Basically, I'm going to assume that we have P pages in the virtual address space. And that P would be a simulation parameter that we can give to a program using command and arguments. I'll show you how it works. But let's assume that you have access to P virtual pages. That means your CPU can generate pages with the page number from 0 to P-1. That's what CPU generates. Also, let's assume that you only have access to 7 allocated frames. That means the operating system has given your process or program 7 frames. That means you have the chance of storing at most 7 pages in memory at the same time. The rest of the pages, if they want to be accessed, they should be brought in from virtual memory, which is the secondary storage, which is the SSD or whatever our secondary storage is. Basically, we have to swap in any other page that is not in the memory. It's not part of those 7 allocated frames, and that's how the program can basically access the addresses that are generated by CPU. The value P might be in the order of millions or 100,000s or something, so it's a big number. Also, we assume that the CPU generates a lot of references. We create a random reference string to basically simulate all the references that CPU generates. That would be randomly generated. It's called ref string generator. It's a very long array of integers. Every element shows a random virtual page number that the CPU generates. So think of a reference string as a long array of integers. The length of that long array would be 1,000,000. So the length of a reference string is 1,000,000. So imagine this is the array with 1,000,000 elements, right? These are all randomly chosen. In order to choose these randomly in a realistic way, I have already done that. I'm going to show it to you. I use something called locus that is moving forward. Locus is basically it's a window of pages that are likely to be referred to in the near future, and that basically simulates the spatial locality of addresses that CPU generates, and that's a very common and important property of addresses that are generated by CPU. Whenever CPU generates an address, there's a very high likelihood that those addresses are neighbors in the virtual address space. And we basically simulate or model that by creating a locus made of a few pages. That locus moves forward gradually. The motion rate of that locus is M. The size of that locus is E. E is not that big of a number. It can be like 10 something. And these one-letter variables are basically the simulation parameters that we can set them by passing some command and arguments to this program's main function. And this locus doesn't only gradually move forward at some rate or with some odd or probability. it can just get relocated to a completely random place in the memory. So this locus can jump to a completely random place. And by the way, this red array that I just draw here, that's the memory with size p from address 0 to p minus 1. The reference string is another array of integers made of 1 million references. I'm explaining how these 1 million references are created. And you don't need to create them. You don't need to randomly generate them. There's a function called ref string generator that generates that. I'm just trying to explain how this random sequence of 1 million numbers are generated. Basically, you know, the locus moves and then the numbers are generated inside the locus only. So I'll show you how it works. After you generate all of these 1 million references or random references, then we are going to implement the actual page replacement algorithm. I'll show you the optimal page replacement algorithm, but it's easy that you continue doing this and generate code for other algorithms like the least recently used or first in, first out or second chance algorithm. Let me clear all of that drawings. Let's get into the details of the algorithm or the simulation test bench. In the main function, I create the seed for the random number generator using srand. That's going to initialize my random number generator. Then I will handle all the command and arguments, and I will basically set the values of these four numbers. E is the length of the locus, M is the rate of motion for the locus, P is the size of virtual address space. It shows how many pages we have. And T is the chance of transitioning to a new locus. Because the probability is going to be a double value from 0 to 1. But, you know, in the arguments, when I'm handling the arguments, when I see dash T, I'm not passing that fraction between 0 and 1. Instead, I pass the inverse of that transition probability, which is going to be an integer. And then I will A to I the argv for that flag. And then I will inverse it by dividing 1 by it. That's the probability. So if your chance is 1%, you need to pass 100 in the argv. So this way, by inversing it, you will get 1%. And after handling all the arguments, if there's an error, we just print this. Otherwise, we print, these are the command arguments. P is the number of pages, locus size, motion ratio, and the transition probability. Then we use malloc to allocate 1 million integers, store it in reference string, and then we use reference string to store all the reference strings, all the random reference numbers. So the reference string generator basically works like this. You don't need to look at it, but assuming that the locus starts from address 0, we have 0, 1, 2, all the way to e minus 1 as the locus. In this while loop, we randomly generate a number. LRAND is a macro that generates a long random integer using the rand function. And then after doing that, we get mod e to get a number from 0 to e. And then we add this with the locus position. And that's going to give us the next reference. If the next reference is different from the previous one, that means the next reference is not equal to the previous reference, which is a stored in reference string ref count minus 1, then we're going to store it. Otherwise, we're going to continue. That's how the reference string look like. If you have like duplicate neighbors, you have to eliminate them because we can just combine the two into one, and then we can get rid of the duplicate. After you get out of this if else after you get out of this if else statement, then we are going to check whether or not we have to displace the locus. If the ref count mod m is 0, that means if we have reached to m, which is our motion rate, then we have to create a random number and compare it with this value. That's like checking whether or not it's time to jump. This random number, let's say if t is 50%, this if a statement basically behaves like throwing dice or like tossing a coin. If it's a head, we do something. If it's a tail, we don't do that. So if the rand is less than this number, that means, you know, we throw a coin and it's a head. So let's move the locus position. Otherwise, don't move the locus position to a random place, just increase the locus position by 1. And that's how we do it. Basically, this if else statement changes the locus position. But again, don't change this one. You don't need to change this. This is basically generating a sequence of references for you in the reference string. After this, it's time to run the optimal replacement algorithm. This is how it works. Some of it is similar to other replacement algorithms, but some of it is only designed for the optimal algorithm. We start a counter called page fault to 0. We're gonna finally print that out and find out how many page faults does this algorithm create, and that shows the performance of that algorithm. The lower the page fault is, the better the page replacement algorithm is. We assume that the frame size, the frames are here. This is an array of 7 integers. Size is an integer that is set to, if you look at here, it's set to allocated frames, which is equal to 7. So size is nothing but number 7 here. We have 7 frames, and then these are some local variables. Page number shows the current page number, frame number shows the current frame number, and car shows the index that we have in the reference string, which is going to move from 0 all the way to 1,000,000. First, we assume that we have pure demand paging and all the frames are empty. Empty means the frame I is equal to -1. If the frame I is not -1, it's a non-negative number like 0, 1, 2, 3. That means it is holding a page, and the page number would be the number that is stored in that frame. So initially, all the frames are -1, but gradually each cell will hold a page number, and that means that page number is in the main memory and is stored in a certain frame. We're gonna fill this. First, we have pure demand paging, so all the frames are empty. Then we're gonna fill them out with the first few numbers in the reference string. How many numbers depends on how many duplicates we have. We start filling that frame list or frames array by using this for loop. We get the next page number from the reference string, and we try to locate that page number in the frames. The locate is a function that linearly searches for a given page in the frames array, and if it finds that, returns the address or index, otherwise returns -1. So it's that simple. We try to locate it. If the location or locating process succeeds, the frame number is not negative, so we are going to subtract 1 from I because we couldn't get a unique page number. This is a duplicate, so we need to go further down in the reference string and find out unique page numbers. We need to look for the first 7 unique page numbers to fill out the frames initially. And then otherwise, if it's a unique one, then there's a page fault because you haven't brought it into the main memory yet. So the frames I will store page number, and then we're going to increase the page fault by 1. Now, the page fault becomes 1, and then we move forward with the next I and next current. So in other words, we move forward in the reference string, and then we move forward to the next frame so that we can fill out all the frames. After all the 7 frames are filled, then this for loop ends. We get to the main loop. Now all the frames are full. Any page fault will cause a page replacement. We need to find a victim, evict that victim, and then replace it with a new one. Because we are using the optimal page replacement algorithm, we need to choose the victim as the frame that is not going to be used in the future for the longest time. That means if you have like 7 frames and you want to replace or evict one of them to bring in a new frame, you need to always choose that frame that is not going to be used in the future for the longest. That's the optimal algorithm, but it's not feasible because you cannot always look at the future. If you look at the past with the similar idea, then it would be a least recently used. If you care about who joins the frames first, that would be the first in, first out. If you give every frame a second chance, that would be the second chance algorithm, which is going to be a approximation of the least recently used algorithm. But I'm going to only focus on the optimal algorithm here, because that's going to set a lower bound on how many page faults you can have. And that helps you to get an idea of what the numbers, the page fault numbers should look like for the other algorithms. In this for loop, I'm going to go through all the elements of my reference string all the way to 1,000,000, get the next reference number, call it page number, then try to locate that page number in the frames. If that frame number is positive or 0, that means the next reference is not going to cause a page fault, so you continue without doing anything. But if it creates a page fault, if the frame number is negative, that means you couldn't find it in the frames. That means you're not finding the page number in the memory, not in none of the 7 frames. So you need to increase the page fault count by 1, and then this rest of the stuff that you see here is only correct for the optimal algorithm. Any algorithm that you want to create must have their own implementation. So, but from line 91 all the way to 105, I'm implementing basically the optimal algorithm. How do I do that? I said I have to look in the future. How much in the future should I look at? I don't need to look at to very far in the future. The limit is enough. What is limit? Limit is a number that is passed to this optimal function, and it is set to e times m. I can tell you why this is a realistic limit, and we don't need to look further than that, but it's not that important. You have to stop at some point. You don't need to go all the way to the very, very end of the reference string in order to find out whether or not a page is useful. But I only set it to e times m. E was the current locus size, and m is the rate of motion. That kind of makes sense because, this is basically how we created or generated the locus in a random way. So we're just multiplying these two. I found a limit, and I'm not going to pass that limit when I'm looking in the future for this algorithm. Anyway, so as I said, we need to look in the future. First, I'm going to create a binary number with 7 bits using this. All the bits are set to 1. 1 means the frame corresponding to that number is unused. If it's 0, that means it has been used in the near future. Then I have a victim integer that is going to keep track of who's going to be the victim. I'm going to look in the future or look in the following elements in my reference string, and I'll try to locate the reference string at index car plus k. K is a number from 1 to limit, and car is the current number. If you're wondering whether this is going to cause a page fault or not, I'm sorry, whether this causes an index out of bound or not, you can make sure by doing this mod a string length. So this way you make sure it never gets out of bound. But you don't need to do that because I always assume that I always check whether car plus k is less than a string length or not. So you don't need that. The code was perfect. So I didn't need to change that. You try to locate your reference string at index car plus k in the frames array. If you find that, then you need to set the flag, the unused flag of that frame to 0. How do you set it to 0? You need to do a bitwise AND operation with negation of 10 to the power of victim. I mean, the bitwise operation is always confusing, so I'm not going to talk too much about it, but you'll figure it out yourself. And basically, that's going to set the victim's unused flag to 0 because we have just used it. After you get out of this for loop, if your unused, if all the unused flags are 0, that means all of the frames have been used, then your victim would be the one that has been used in the very last iteration of this for loop. So that would be the victim, because the optimal algorithm works in the following way. You need to find out who's going to be referred to the latest in the future. That victim is going to be the host of the new page number. Otherwise, if there is some, or at least one frame that have not been used in the future, the victim would be that one. So how do I find which frame hasn't been used in the future? I would basically check out the unused bits, and using this while loop, if I find the index of the bit that is not 0, I keep dividing the unused by 2 and check the mod by 2, and then at some point I will find the victim, and when I find it, then I will say, okay, that's the useless frame that's not going to be used in the future, so I'm going to replace that with the new page. And then I return the page false at the end. That's pretty much it. I'm not going to run it. You can run this. Let's say if you want to run the first scenario in the assignment, you can run it by passing the following command and arguments. I have put it here. This is for scenario 1. The P is to the power of 20, which is 1,048,576. M is 200, E is 10, and T is 0.05% or 0.0005, but you need to pass the inverse of that, which is 2,000. And that's how you run one scenario, like scenario 1. You have a total of 5 scenarios, and then for each algorithm, you need to run, for each scenario, you need to run this once. I already have done the page, the optimal page replacement algorithm. For other ones, just add to this main. So keep that random reference string. Don't change it. Just call more functions for the other algorithm. For example, similar to this, call another function called LRU, and pass the random string the number of frames. And if you need some other information, pass that And then do the same thing for other algorithms. And then print out the number of page faults for every algorithm, and that would be good enough for doing the assignment. Thank you.